All right, welcome back to data science course study we have been looking at for some times now. Today, we want to continue by looking at non-parametric tests. I've tried to explain what it's all about in the uh, last topic we discussed, and before we went into parametric tests. So when the parametric test fails, or the assumptions of non-parametric test fails, then we can deviate into non-parametric tests. So every parametric test has its own counterpart, non-parametric counterparts. Okay, we're going to look at each of them one by one, apart from uh, chi-square, which we'll not be able to look at because I told you before, I said before, chi-square uh, could basically be used on both sides. Okay, so you don't need to look at that again to minimize the repetition. And we want to look at our library first. We have a common library. We want to use a gapminder. This is where our data set will come from. And we also have a library called tidyverse, which I've been using before. So we're going to load the total library now. All right, so after loaded them, we need to describe what is inside this gapminder. Gapminder. Let's just glimpse it. Okay. Okay, so I run the gapminder now. So I just want to glimpse what is inside it. All right. So now it has a 1704 rows and the 6 columns. Columns consist of a country, continent, year, life expectancy, and the population and GDP per capita. The GDP per capita is actually the income of each country within that particular year. So we can check further by just typing here. Let me just say, okay, let me stop here. Okay, let's just say gapminder. Let's see more about this data set. Okay, you can see here talking about gapminder data description, excerpt of the gapminder data on the life expectancy, GDP per capita, and population by country. All right, so we have each of the parameters. I mean, variables defined here. We have country factors within 142 levels. We have continent factors within 5 levels. We have year ranges from 1952 to 2007 in increment of 5 years. All right. So for every 5 years, we measure the population, we measure the income of the country. So I mean repeatedly. So we have life expectancy at birth in years. We have population. All right. We also have GDP per capita. This is the income of that particular nation for that particular year. All right, of measurements that is measured. All right, so this is in dollars, in US dollars. All right, so take note of that. So because this is a metrics, this is a metric, okay? It's in US dollars. All right, so this is what we are talking about now as a data set. All right, so we have seen a brief description about the data set now, so we can go back and see what to do with data set, because we need to first let's first attach it. Okay, already around here. I don't need to attach anymore. So already around, so just leave it this one. I just click on attach here to attach my data set. Don't forget, I told you why we attach, so that you only remember why we attach our data set. Already attached now. Okay. All right. So because already attached, you can go ahead now. The reason why it's attached is because we don't want to use $sign to call our variable or columns one by one. All right. So instead of using I can say gapminder, for example, gapminder. Okay, dollar country. I don't want to do second. I don't want to do that. Okay, I want to supply country straight. So if I just say country, okay. So if I need country, I just say country. All right. This is the country for me. All right. So that's what I want to. That's why I don't. Attach the data set first. All right. So later, if I need, I can detach it later. All right. So that is that for that. Then let's summarize the data set first. Let's summarize. Let's see what is inside. All right. Okay. Let's summarize. We have a country. These are 12, 12, 12, and others are this. Then we have continent. Right, Africa, Americas, Asia, Europe, and Oceania. Right, we have year from this to this. We have life expectancy. Okay, this is the minimum, maximum, mean and median, first quarter and third quarter. We have population of the country, and we have income, GDP per capita of the country. So for that particular year, so these are the here there's no missing value here. Okay, so you don't need to bother about missing value at all. All right, so what you need to check some assumption to see that the data set meets what you are looking for. Okay, for example, now we need to check. Let me plot. Let me try and see if I can plot. Okay, so let's plot ggplot first for GDP per capita. So this is what we got. Okay. All right. So you want to check also life expectancy. Okay. You want to I try to plot density plot for both of them. Okay. This is what we got. Density plot. So we want to further check our QQ plots. Okay. I'm trying to use a log to see if it can be better. Okay. But let me try the log first. You see, it's not you can see. So it's not perfect here. You can see it's like it's coming out here. So if you look at the histogram, okay, let's look at the histogram. When we log the histogram, a little bit closer, but not exactly. Look at the box plot. Box plot is okay, even though it's skewed here, but it's okay. So, but we cannot conclude. You can see that our QQ plot is not okay, our density is not okay. All right, even though box plots look a little bit okay. All right, so but we need to check also by using Shapiro test to test our test for normality distribution. Okay, so like as usual, I've just supplied Shapiro test. You can see it's significant, which shows that it is not normal. Does not follow normal distribution. So let's put last expectancy here too and see. Also same, they are both significant, which means there's no assumption for normality here is not valid. So we have to go for that. Let's also test for levity test. This for homogeneity of variance. Okay. All right. So let us check by supplying the continent as our distance. So let's check this first. Run this line first. Highly significant as well. So which means it's not homogeneous. All right. Let's also look for life expectancy. Right. Significant as well. So overall, it shows that this particular data set, even when we try to look at this, even this particular one, let's look at this. Can see that our mean, which is red, is greater than the median, right? Okay, which is blue. All right. Obviously, if you also run life expectancy here too, okay, you can see also they are not equal. and by our normative assumption, they must be equal. They must lie on the same plane. They must be equal. So all the tests we have run so far shows that this particular data set is not normally distributed, does not follow homogeneity of variance assumption. All right, so the two tests already failed, both graphically and numerically. So we will not be able to use a parametric test for this now. So we can now deviate to non-parametric test now. So that is one of the reasons why non-parametric test is very important. Whenever the assumptions is violated for parametric test, then that does not stop the research. Okay, it does not stop the work. So we have to switch over to non-parametric test. All right, now let's now look at non-parametric test step by step, and starting from the first one we call single sample. All right, single sample. We have single sample test as well. Don't forget that, which we did before. So, but under parametric, but under non-parametric test, we see apply the same thing, but in this time around, because one thing you must understand about non-parametric is that it doesn't use mean as usual for parametrics. It uses median. All right, because it's ranked. It's operated by ranking. They rank the data, okay, from the lowest to the highest. So you rank the data, and they uses the data by following the median. If it's a mean that which is used by parametrics use usually mean, but non-parametrics use median. All right, because it's based on ranking. All right, in this time around, now we want to look at the t-test also, single t-test, but in this form now using non-parametric test, but we are going to use what they call Wisconsin signed rank test. Wisconsin signed rank test. So that's what we are going to use. That is that is a replacement for one sample t-test. Okay, one sample t-test also is rank t-test is a non-parametric alternative to one sample t-test, which we have just explained. When the data cannot be assumed to be normally distributed, it is used to determine whether the median of the sample is equal to a non-standard value. Last time we talked about mean is equal to a theoretical or a reference value. We have a reference value that we already know, already been given, which we want to test our result against to know if it's true or not. That is under t-test, but same thing applicable here. We have a known value as well, which is called reference value or theoretical value. But in this case, it will be using median now, not using mean. There, it was mean we used the other time under parametric test for t-test. Now we're using median to test. All right. So, for example, now this is dealing with one numerical variable, okay, which mostly supposed to be a continuous variable. To compare, definition is simply means to compare a sample of a single value, okay, sorry for that, of a single value. All right. Now we have a question which you want to start with. Let's look at a sample question. For example, is the median life expectancy equal to zero? Okay, don't forget we are not dealing with mean now, we are dealing with median, so you have to understand how the question goes, because the question will always tend to median sometimes, or just differences. Is the median life expectancy equal 0? All right, about equal median now, equal median, or equal to 50 if we set our MU to a reference median or to a theoretical median. Okay, let's say we have a reference median called 50. We can set to 50. All right. So that is, we are looking at the question like that. Okay, is the median life expectancy from our data set? Don't forget. Let me scroll up again and show us our data set again, so that you can understand where we are coming from and where we are going. All right, we have okay. Let me just clear the screen. All right, and let me just glimpse again. All right, let me glimpse again. Gap minder. Right, so look at it again. We have that's it. We have country, we have continents, we have year, we have life expectancy, we have population, we have GDP per capita. So our major work we'll be looking at is life expectancy, income, which is a GDP per capita, and also maybe sometimes we look at the continent as well, continent, and sometimes country. We look at country as well. So as our group variable, factor variable. So now, based on this question now, we have a reference mean set, for example, 50. Let's say we say 50 is our reference mean, all right, which is our life expectancy. We have expectancy here, 28, 30, 40, 50. But we want to find the median, all right, not mean this time around, median. We're trying to say, okay, we already have a reference mean which had been proposed by somebody, or which we have assumed to have known. Okay, that we have a reference mean of 50. You want to know, is this 50 of reference mean you have, is it equal? Okay, is equal to the median of the life expectancy we are looking at? All right, so we have to set that here. So let's say we have a hypothesis now. We have H naught, which is and the H A, and we have both a null hypothesis and the alternative hypothesis here right now, H naught or HA. So you can call it HA or H naught. Both are correct. H1 alternative hypothesis or H1. So both of them are correct. So we have we want to say that the median life expectancy is 50. That is our H naught or null hypothesis. We can say that the alternative say the median life expectancy is not 50. So we have to test. But let's say we want to make it more appropriate now this time around. Okay, let's say we want to look at a median life expectancy in Africa. Okay, the median life expectancy in Africa, let's say in Africa is 50. Okay, all right. So let's say let's define the question again. In Africa, right, equal 50. All right, equal 50. So now we our hypothesis now question. So let's say we select, let's use our piping now and select our data set now, single test gapminder. So we pipe in our data set now as usual. All right, our data set, we pipe in, we filter by continent, Africa continent. So we pipe in also, we select our life expectancy, because that's what we need. Okay, we need that to test, find the median, to see if the median is equal to 50 for life for Africa. You can use other country anyway. Okay, you can use other country. We have many country here, right? I mean, other continents rather. We have many continents here. Like okay, we have 5 here, so you can use any other continent. So let's run this line first. Let's run this first and see. Okay, I run this. All right, so it's run. Then we can now go further and supply our test. One sample the test now. I mean, using the constant now. So the constant of test, that's our keyword. This particular function is supplied. Okay, or we dot test. So we're passing our new variable now. This variable is now a new variable. So you can actually see this variable actually. Let's see this variable. Let me run this. All right. Let me run this line. Okay. Or let me select first 5. Okay. Let me say, okay, let's do like this. All right. Okay. So we want to see the first 6 now. All right. Let me run again. I'll come back to that later. Okay. So let's just run this line, only this guy. I want to see what it look like. All right. So look at what it look like. Look at it. So right. So you can find the remedial as well. So but let's just now let me now remove this guy now. Okay. I remove this as well. All right. So let me rerun the test again. So this is our new variable now. Okay. This is our new data set rather. This is a new data set now. If we have been passed to this, all right, because we have filter based on Africa only, all right, to test. Okay. So we have selected life expectancy only also. So that's what we have in data set, new data set now. So we are going to pass our data set here, dollar, right? So because we are dealing with a new data set now, not gap. If gap minder will have supplied just like life expectancy rate, which would have been very easier, but I don't want to do that because it will be wrong. I just take my data set, which I newly created now. I pass it here, dollar life expectancy, which we have here, right? We set our MU, is our reference median, all right? We have now equal to 50. The default is 0, actually. The default is 0. Same way we have it in a parametric we have here. So the default is always 0, but if you don't have any reference value or any theoretical value, the default is 0. So we can supply 0 there, but now we already have 1, so we just supply 50 and we run this line. All right. So this is our result. To show you our result here. All right. We have p-value very significant. All right, which is so alternative hypothesis 2 location is not equal to 50. Right. So we can go back to our now assumption now, our hypothesis now. The median life expectancy in Africa is 50. The median is not 50. So now, because our value is significant, this p is less than 0.05. You can see it's less than 0.05. Then we can reject null hypothesis that says our median life expectancy is 50, right? And we do not reject median life expectancy, which is not 50. We don't reject because it shows here it's not equal to 50. You can see that, right? So we take alternative hypothesis, we reject a null hypothesis. All right. So it's as simple as that. Actually, it's as simple as that. So if you want to test whether the median life expectancy is less than 50, if you want to do one-tail test, okay, one-tail test, you can do that as well using the same method. So we use this formula, okay, the same formula as a test. We pass here, mu equal to what, 25. Let's assume that is our, we want to say less than or greater than. Both of them are possible. They are both possible here. So you can say, we say alternative equal to less. All right. That means we are looking at a one tail now. All right. This is just a two tail. Just finished now. But you want to do one tail. One thing is mean that you are dealing with one side of the density plot, for example. Now one side of the tail. So we just it divided into half. So let's say that the life expectancy is greater than 50 or greater than so amount. So we can pass that amount here, which we are saying we are mentioning here. Then we can say less than. If we say we are using less than, if greater than, we say greater. Yeah. All right. So that is how to do one tail test using the Wilkinson as well. So it's as simple as that. So you can report further on this, okay? Because now by rejecting null hypothesis, we can conclude that the life expectancy in Africa is not equal to 50. I mean, median life expectancy in Africa is not equal to 650. That is what it meant. So we can go further and now test also for another test for two independent variable now on pair. So this on pair now, all right, which is called, we are going to use what we call Mann-Whitney U test. U means on pair, okay? On pair test, as a U here. All right, so that is Mann-Whitney. So this is one numerical, one categorical. This is called two sample test. Don't forget what we just finished now is one sample test. So this time around, the same sample test we have done before in parametric now, we want to do here now, using what Mann-Whitney UT test, okay? U test rather. So this is using two independent, all right? So we have done that before, but we want to repeat it here again. The definition is that this is equivalent to the independent two sample test, all right? It tests for differences between two unpaired samples, all right? You remember two unpaired samples we have done before. Same thing applicable here. Since the Mann-Whitney U test only compare two samples, all right? We will focus on the Ireland and on Ireland here and Switzerland, Ireland and Switzerland to illustrate this test. Okay, we have Ireland and Switzerland. All right. So let's say we want to compare the mean of life expectancy by country between Ireland and Switzerland. Alright. Alright. So these two countries now, I want to look at it. So alright. So let's come up with a question. Is there any difference in the life expectancy between Ireland and Switzerland, between these two countries? Is there any difference in their life expectancy? Okay, that is our first question now. Want to consider. Then let's create a null hypothesis from that question. If you say the life expectancy in both countries is the same or zero, no difference. Okay, that's our null hypothesis. Okay, alternative say the life expectancy in both countries are not the same. All right, so we want to test if they are the same or not using our Whitney test. Okay. All right, so let's also use our piping again, and let's say we create a new object here called unpair country. So our data set is piped in. All right, we filter by country. Okay, country in Ireland and Switzerland. All right, so we filter first using this function, using this in, okay, for filtering a parameter. Then we just filter only these two countries. Okay. If you want to use other country, you can just apply it here, right? Just to test to see the result. Now, don't forget this country is a factor variable, or rather, it's a categorical variable. Don't forget. All right. You could use continent as well, but I want to use country now. Okay, so let's supply we consider test here now. We have our let's better see here, right? And we have our country here, which is a categorical variable. So don't forget, when we started here, we saw that we have one numeric and one categorical. Okay, don't forget. So, and this is a metric based numeric, and this is a categorical variable, right? So our data is on pair country. This is our new data we created now because it's already filtered from Gapminder. We have filtered it. So we have a new data set called unpaired country now, because when we filter it, we assign it to an object called unpaired country. So we have assigned it to it. So we have a new data set which is filtered. So we can also fill it also as well, like we did the other time. So let's fill it and see what I'm talking about. Let's just fill it. Let's just fill the first 5. All right. If I run this line of code now, should give me a first 5 now. Let me run this guy. All right, so look at what we have. Country, continent, year, life expectancy, population, GDP. So based on Ireland and because we only filter first 5, okay? That is why it's giving us only this one. So if you want to, first 6 rather. So if you want to see the rest part of the Switzerland, you can just maybe few more, search for more, or filter display more. So, but we don't want this. Let's remove this guy just for the purpose of viewing our record. All right. We can also do that. We can also do like this. We can run this line of code again and use our view. You can say view. All right. Let's try this and say view. All right. We pass our unpair country here. All right. So that you can see using okay, if you run this line of code now. Okay, so you can see here. Okay, so you can scroll now, can see very well now. So you can see the both of them. All right. Yeah, so that's what I'm saying. So now you can see clearly now. It's very clear now. So just use that view to see. All right. So now we don't need that. We don't need this. Okay, just to view our data. So you can easily view. You can even plot. If you want to plot, you can plot it. Okay, and box plot. If you want to plot it. All right. So we have done that in the past many times. So I don't think it's necessary for now. So let's just go ahead. Let's pass in our data here and pass this one. Let's run the analysis. Okay. All right. So we run the test function for an embedded two-sample design works just like the corresponding analysis with the t-test function. The first argument should be a formula, and the second should be data frame containing the relevant variables. All right. So let's read further. The man-Whitney test is also called a two-sample recursion test. the formula life expectancy that we supply here, this formula we supply here, all right, works in the same way as other statistical function in R. The variable containing the value we wish to compare, which is this, is on the left hand side of the this symbol here, and the variable containing the group identity, which is country, belong to the right side. So that is what we just apply here now. So the output from the result here is similar to that produced that produced by the t-test function. At the top, we see a summary of the test and the data. The life expectancy were not significantly different between Ireland and Switzerland. So if you look at the test we have here, our result is say giving us this here. Okay, p value is 0.14. So alternative hypothesis say true location shift is not equal to 0. So which means it's not significant. All right. So we can now because it is not significant, we can reject alternative hypothesis. Reject this. All right. We reject the alternative hypothesis that says the life expectancy in both countries and Ireland are not the same. Because it's obvious from here that they are the same because it is equal to 0. I mean, it's not equal to 0 because it's not significant. All right, which means we do not reject not hypothesis now. We don't reject not hypothesis. We do not reject this. All right. Don't reject it because this is the life expectancy in both countries and is the same. Okay, it's the same because or 0, but because it's not significant, right? So we have to we do not reject this, okay, but we reject this, okay, we reject this. That says that they are not the same, all right, because it's not significant. All right, so that is how to test for that. And if you go further, you also see that we also have what they call Wisconsin paired sample t-test. All right, we have done that also in the parametric, so I've explained that there. But we also this which is also equivalent to dependent to sample t-test also in a parametric test to test for differences between pair samples. All right, pair samples. You can develop such questions. Is there difference in life expectancy in Africa between the year 1957 and 2007? Now, don't forget that dependent to sample t-test is based on time. All right. Maybe you want to test, want to know the effect of diet on a patient, on a individual, for example, on participants. Before the diet begins, you just you test their weight, all right, or their health. Then after the diet, you also test again. Maybe after 1 week or 2 weeks, or 2 weeks or 3 weeks, you test again the same participants. Okay, you test again. So you have what they call pair samples. It's called pair samples. It's called dependent to sample sets. Okay, so in this case now, you can now calculate, you can find their pair sample test. Okay, if there's a difference in the life expectancy in the if there's a difference, okay, if there's any effect difference in the diet, all right, or maybe you want to test, for example, stress vacation on a stress level. Okay, is there any effect of vacation on stress level of patient? Maybe maybe before they travel, okay, on vacation, you test their maybe BP or stress level, all right, and then when the same participants, okay, when they go on vacation and they return back, you test again whether something changed. Maybe sometimes maybe because people have been overworked, they have been stressed so much, all right, and their BP is very high. But when they go on vacation, maybe they have become relaxed, they have rested, they enjoy nice meal, nice outing, and the rest of them, and they have become refreshed. And when they return back, the result may not be the same. That means that particular vacation may have effect on their health or on their BP. So So it's an experiment. So that is called paired sample, okay? Because you are dealing with the same participant, but two tests is carried out now. It's similar to a single test actually, but you are carrying out the test twice. That's all. The difference. Okay, it's similar to single sample test. Okay, but this time around now, what is a pair because you are carrying out the test in two times, two different time. So it's time based. Okay, he's dealing with time. The first time, the second time. Now we are looking at a life expectancy, for example. You can look at the GDP per capita as well in this year and this year. All right, we can do that. Okay, maybe we measure GDP per capita of the country in 1957. Okay, we now wait again till 1958. The same country also will measure their GDP per capita as well. All right, in 2007, we want to see is there any difference in this particular GDP per capita. Okay, or we want to look at a life expectancy in this year, in this continent. Okay, in this year. Okay, we waited for another year. Okay, we test again, we check again and see if there's will be any difference in 2007. All right, so that's what we are doing now. So it's the same thing, just as a data set is not the same. All right, so the difference in life expectancy in Africa between the year 1957 and 2007 is zero, no difference. That is our H0 now, our null hypothesis. The difference in life expectancy in Africa between the year 1957 and 2007 is not the same. It's not zero. I think there's a difference. That's what we are talking about now. All right. So let's carry out the test now. First and foremost, we want to first filter as usual. Let's call it our subject called paired year. So we call our data set gap miner. We pass the piping in. Then we filter by year, this year and this year. All right. Don't forget, this is just 2 years. It is called paired test, not more than 2 years. Okay. If you do more than 2 years, you're going to have error. There's a room for that for another method. Okay. All right. So the same way you do for dependent test. Okay, it's the same thing you do here because that one's also two. Okay, 2. If you want to do more than that, you have to use an over to go beyond that. All right. So now we have filter here. We have continent is based on Africa. Okay, so this condition is true. Filter year in this year and continent Africa. So we have filter. We mutated year, factor it. We have level these 2 levels. Okay, all right. So don't forget, I've done mutation before. All right. We want to create a new variable called year. So we want to factor this year, our year you have here. We want to factor it and make it a 2 level. So this year we pass it in here. Levels. You can use another name to call this year if you like, but you still want to call it year. All right. All right. So because this year is one we pass here. Okay. To level this one 2007 to 2000. So we just rearrange. No, there's no problem here. Now we group by year. Let's say we group by year. All right. We group by year. Then we summarize median. You can find median. This is just so. These are not necessary actually. You can stop here. Okay. This is what we need. This is all we need. Okay. That is all that we need. The rest we are seeing here, I purposely put them there so you can view the data. Okay, we can filter and view. That's what I put. What we need is just that selected area. That's what we need. Others one we don't need them. All right, we just need to filter our data set. That's all. To create a data set, we need to filter. So we have filtered. We have this, and that is all we needed. Now I went further to do this because I want to see the output first before I run the experiment. Okay, so what do we do? I run everything here. All right, I run this. So I want to see the median. I want to group the median of life expectancy. I want to group the standard deviation and I want to count. All right, I want to count the total numbers of in 1 year, total number for 1 year per year. So let's run this analysis. If I run, I've run. Let me see what is inside now. You can see year 2007. We have a median life expectancy 52.9, standard deviation 9.63, total is 52. Year 1957 we have 40.6, 5.62, and total is 52. So the total must be, the number must be equal. Okay, that's very important. The two must be equal. That means the same number of participants we tested before the experiment, the same number we tested after the experiment, after the other time. So you must understand that that is paired. All right. So that is what exactly we are doing. So we are actually dealing with a life expectancy, although the same continuous variable we are passing here now. So okay, now we have we consider the test. Now we pass our parameter, our metric test here, metric variable here. Then year, the year become our group data. Okay, because we are dealing with a two. Okay, this year and this year only. All right, we say pair equal to true. All right, our data is passed here, which our new data set is this. All right. So, but we're not using this one now. I'm going to run again before I'm going to run again this line. Oh, that's what we needed. We don't need everything here. All right. Okay, this one will not give us accurate result. We don't do everything here. So we need only this line here with this point. All right. I will run this one only. All right. So let's run this line. All right. So we now pass this one now. I will pass it here. All right. So that this one just focus of viewing. So let's run this line now. Our test. All right. What we got is that our p-value is significant. All right. It's significant. So which means that we can go back to our test and report it. Okay, because it's significant, we do not reject null hypothesis, right? I mean, we reject rather null hypothesis. We reject null hypothesis that say the difference in life expectancy in Africa between year this and year T is zero, no difference. Now, because it's significant, it means there's a difference. Okay, it is significant now, less than 0.05. It means there's a difference. So we do not reject alternative hypothesis, right? Because it's not equal to 0. So the difference in life expectancy in Africa between this year and this year is not equal to 0. There's a difference. So it means there's a difference in the life expectancy in Africa between this year and this year. There's a difference. So if they are equal, then it means that this is true. But because they are not equal, this is true. All right. So we reject null hypothesis now in the favor of alternative hypothesis. So that should be very simple enough. Okay. So let's go further and also test for the ANOVA part of it. So we want to look at one way ANOVA, okay, as we did also in a parametric test. So we are going to use what is called the Kruskal-Wallis test. Okay, this is comparing the means of more than two independent groups. But don't forget now, that is what it does actually. But here we are comparing the medians now. Okay, medians of more than two independent groups now. Okay, that is what we are doing for Kruskal, because don't forget they based on parametric based on median. Okay, because it's using ranking. Okay, the Kruskal-Wallis is equivalent to one way or another. It allows us to test for difference since among more than two samples. Okay, this is more than two samples now. So you can have a question say, is life expectancy in these three continents different in the year 2027? Okay, we are dealing with more than two samples now. Okay, more than two groups. Okay, the life expectancy in the three continents is exactly the same in the year 2027. That is H0. So, but H1 here, let's say that the life expectancy in the three continents is not the same. There's a difference in the year 2027. So we want to look at it let's do as usual and filter. Let's say we create another data let's call it gap data. All right. We'll have changed the name as well. So let's filter here our data set. We filter by year 2027. All right. Only the continent we are looking at is America, Europe, and Asia. Three continents. Now, this is for ANOVA because this is more than two now. So okay, three or more. That is what ANOVA does. This is one way ANOVA now. We have 3 or more. This is more than 2. All right, so this is we have America, we have Europe, we have Asia. So we can select by continent and life expectancy and see the result. If you run this line now, you can see the result as well. All right, so let's see the result here. You can see continent life expectancy. We have Asia. We have so we have it selected here. You can see we have 78 more rows. All right. So that's what we have. So now we can now run our critical test now. Okay, we can see this is our new data we have created here, but we have used to filter. Then we also have a continent here. Okay, we have our data here. So if you run this line of code, don't forget our hypothesis here. All right, so let's run and see. All right, so life expectancy by continent, Critical Wally chi-square equal to 21 points. So that is our Critical Wally Wally's value. The degree of freedom is 2. P-value equal to significant, so 0.000202. So this is significant, right? Highly significant. So which means our P is less than 0.05. Excuse me. Our P is less than 0.05. All right. So what can we report here? Because this is significant. Now we can now go back to our hypothesis and reject. We have to reject null hypothesis now. Why? Because our alternative is true. Okay, it's significant. It's true. It means life expectancy in 3 continents is not the same. There's a difference in this year. You can change the year to another year and try to see the result, because who knows? they may be different. All right, there may be. Let's just use another year. Let's say we use year. Let me see. Let's say we use year 1992. For example. We run this again. Just try to test now. So we pass our distance again. Let's see. Is it significant? All right. So you can play with the year actually, because sometimes it may be different. It may be the same, by which you can reject a hypothesis. All right. So that is what I'm trying to say. So you can go for that also and do what is called one-way repeated measure ANOVA. So that is when we have a Friedman test. Okay, Friedman test allow us to do repeated measure ANOVA more than 2 dependent variables. Okay, so this used when several measurements of the same dependent variables are taken at different time points or under different conditions for each subject, and the assumptions of repeated measures ANOVA have not been met. All right, let's say we want to assess whether there is any statistical difference between, maybe there is any statistically significant differences. Okay, let me use, let's say, differences between the distributions of the 3 or more peer samples. Okay, in the 3 different years. Okay, we have the different years. We want to see if there's a difference, okay, between the distributions of the 3 or more peer samples, right? So that is so this one is dealing with a repeated approach now. Okay, so let's say we start a such question says, is there a difference in the life expectancy in Africa between this year, and this year? All right. So now the problem, we have done one before. Don't forget. Okay, let me show you again. I think I should remember here. We dealt with one here. All right, this one. All right, this one only can see that we call it, we consume peer samples. Okay, This is a peer sample dependent test. But what if it's more than 2? This one did only 2. That's the difference now. Okay. What we are doing now is the same thing we are doing now. We are still doing again. But now this is when this particular peer sample is more than 2, it cannot be handled. All right. By with constant peer sample test, we have to use another method. So which what we are doing now, okay, it's more than 2 like this number. So we are dealing with a 3 or more. So you can still make it more, okay, but at least it's more than 2. All right. So you say the difference in life expectancy in Africa between the year this 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 is not is 0. You should know difference. All right. The no alternative say the difference is in Africa between this year it's not, it's 0. There's a difference. So we want to now create now this one is different now. So because we are having 3 continents, and I want us to see the result, how it is arranged in form of year. So that's how I break down this in 3 parts, okay, before I combine them together. So there's a method that you have to follow for this, okay. So now let's say the first want to we filter the first year 2057 by using gapminder. We pipe in our gapminder, we filter, okay, year equal to this, and continent is Africa. Don't forget we are dealing with Africa as a continent. We mutate, okay, let's call it y57 equals to life expectancy. All right, we assign this now to this, I assign this to this, okay. We now select this. We want to make this a new variable now. That way we are creating a new variable called y1957, year 1957. That's what it means. We are creating a new variable. So our new variable is assigned to this. So our life expectancy is called for life expectancy for this year. That's what we are saying. Life expectancy for this particular year. Okay, that's what it means. All right. So we select that particular life expectancy for that year. Okay. The same thing for 1992. We do the same thing. For 1993, for 2007, we do the same thing. All right. So don't forget what it means here. It's still talking about life expectancy for this year. What it means. So we want to fill. So let's first fill the data. Let's say we create data equals to data.frame. We pass the first one. This first one we created here. We pass it in. We pass the second one in. We pass dot one in. Data frame. Okay. So we create a data frame now in that. So if you run this line of code now, you can see that this one is okay. Let's run this first. We have not run this. Run this 3 line. Okay, this is line. Want to do this line first. All right, we have run this 3 line. So let's run this line data called data now. So we have our data now. Let's look at the bus plot first. All right, look at the bus plot. This year, this is the life expectancy. Okay, for this year. Here we can put that 2 years life expectancy here as a x-axis. All right. So that is what I'm talking about now. So I hope you understand what I'm saying. So you can put title here, okay, on that title here, I say life expectancy. Just say main, just say command main, x-axis, y-axis, s-lab, y-lab. So, but we don't need to go to the details now. We already know that this is a life expectancy for this year, life expectancy for this year, for this particular year. All right. So we have to combine the matrix now, okay, because we are dealing with Freeman have different approach, okay, from others, different approach. There are 3 ways you can approach it, but this is one of the best way, okay, because of the type of data we are dealing with. So we have only 3 peer year now. This year, in this year, 3 years now consecutively. No, so we have sample. Let's create an object called sample. Our matrix year, this year is pass n column is equal to 3. Okay, if you have 4, you pass 4 year, right? So we are creating a sample matrix now. So we run this line of code. You can see it's already created. So now let's call run our test now. Friedman.test. We pass the sample here. All right. So that's what we are doing now. So don't forget, if you want to check the sample, you can check the sample now. If you run this line of code now, this line, let's say sample. Let's run the sample. Let's check the sample first, or the year. Let's check the year. Let's say head data. All right. Look at what I'm saying. Look at it here. See this life expectancy for this year, okay. You can see them. All right. So you can see do better, but I'm trying to not to make it too much complicated, okay. So you can run the test now and see what I'm talking about. So let's run. We have non significant. All right. You can see Friedman so that it's not significant, 0.5, which means we go back to our hypothesis now, right? The difference in life expectancy in Africa between this year, and this year is 0 or no difference, because it's not significant. It means we reject alternative hypothesis, reject this, right? Don't forget this one we have done before that time is different. It's different from this one, right? It's not the same, okay? So this one is different. All right. So we reject alternative hypothesis. Okay. We do not reject a null hypothesis. We do not reject this because it is significant, which means it is not significant rather, which means it is 0 or no difference. That's what it means. No difference. It means there's no difference in life expectancy using a Friedman test. Okay. It means the mean of this rank, they are equal. That's what it means. No difference for this year, this year, this year, or in Africa. Okay, they are equal. Right. So that is exactly what he's talking about. So the report shows that there is no actually significant differences between the distributions of the 3 PS years. Okay, therefore, null hypothesis is rejected, and in the favor of what? Alternative hypothesis. So that is exactly what we do. All right. So I think that one is simple enough to follow. Okay. Right. So let's look at a Spearman rank correlation. We did correlation the other time. It is called a Pearson, okay? Because that is under parametrics. But under non-parametric, we do Spearman. All right. So Spearman rank correlation test for the association between 2 numeric variables. It is equivalent to Pearson correlation that we did the parametric. All right. Let's have a research question called: is there any relationship between GDP and life expectancy in year 2027? Okay, we are trying to pull out based on this year. Okay, so you can pull out another year you like or you want to use based on your search question. All right. Let's say we have our null hypothesis called there is no relationship between GDP and life expectancy in that year. Okay, or we can say no alternative say there is a relationship between GDP and life expectancy in that year. So how do they relate? Is there any relation between GDP and the life expectancy during this year? So we need to filter based on that year. Okay, as usual, we filter. Let's say we call it my gap. We use our gap minder here. We filter by year 2027 only. Then we select GDP per capita and life expectancy. Okay, based on this year only. All right. So we are filtering now. So if you run this line of code now, we filter here. All right. Then we now pass our correlation. So now because we had a new data set here now, which we have filtered. So that's what we use here. All right. So it has this and this inside, 2 variables. So we have call.test. Now we use this method. Okay. Then this symbol must be here. Then say my gap dollar per capita. Okay. Plus my gap dollar life expectancy. We pass it here. Comma. Method is equal to Spearman. Data is equal to my gap. Okay. So we pass our data here. All right. Which shows that this data set is coming from this particular data set we have just created. Then we run our experiment by supplying Spearman as our method of correlation. So if you run this line of code now again, all right, you should be able to see the result. I see the result here. This is significant, all right? In fact, our estimate is 0.85. So there's a difference. These are our correlation now. Okay, so this is our R, 85.65. That is a 86%, approximately 86%. All right. So we have approximately 86%. That's what it means. 86%. So we can go back to our and say, because it is significant now, we reject a null hypothesis. All right. As I say, the relationship, there's no relationship between them. I mean, there is, but the relation is very high. 86% is a very high relationship, very high. So we do not reject this. Okay, we do not reject it. We reject only this. There's a relationship between GDP capital and life expectancy. So we can plot and see we can plot here simply just a simple plot here, right? You see, look at it, plot here. right? I log this so that it can do more appropriate. Okay, so that's I log it. So we can supply title left as so that's no problem. So we can supply that too. You can see so that relationship. So you can also do further. Maybe you just want to make it more make it more look good by supplying other parameters. So we run this library as usual. We have done that before many times. So we pass we do our ggplot. My gap is our data set we have created here. This one we pass it here. All right. We log our income and our last expectancy as y-axis. Okay, so our GG points is here. Our start is called here also. Then we run this line to see the result. All right, you can see here. So don't forget our R is 0.81 p. Okay, so this look at it. You want our correlation, but this is our R. Okay, so p less than 0.01. You can see our p is also significant here, less than 0.01. So this is what we are talking about now. Okay, if you zoom out, this one can be used in an analysis, right? You can see make it the graph look better than this. Okay, so if you want, but just want to see analysis in a simple form. So that is we can detach our Gapminder now. You can say detach Gapminder. No. So if you run this now, detach it. So it's detached, so that you will not be using it for something. So now we are able to cover the non-parametric test, which is equivalent to the parametric test we have done before. All right, so that is what we are able to do today, and I hope that you understand this. And the next class we will do more and look at other areas of this course as itemized. So I will see you in the next class. Thank you so much for your patience for listening. I will see you in the next class.